Okay, so in this video clip, I'm going to follow in line with Halvarian, right? Paper, Big Data, New Tricks for Econometrics. And we're going to set out, just grow a tree, classification tree for survivors of the Titanic. Now, in this instance, I use a slightly different set of data compared to Halvarian's tree. Here he excludes the NA variables from the data set, and so only has, I think, 1,046 observations. I used the full data set. I didn't exclude in the code that I have in R. I include in the full 1,309. So there are some differences. Also note just an explanation of why this type of tree. So it's a decision tree, and the idea here is to explore some of the non-linearities that exist. So we have a discrete variable, and the discrete variable is either survived or perished on the Titanic. And it's a 0-1 outcome, and that's something that is common now in statistics, because very often either the potential customer clicks and makes the purchase or doesn't. So we've binary outcomes. We wanted to set out some kind of framework where we could divide into categories, and this classification problem is sometimes used for spam, in classifying email into spam or not spam. So there's many applications of this more widely in data science and of course in economics. When we have this type of data, we've been working with dependent variable that is binary, 0 or 1. Economists normally, and generally statisticians to some degree, economists would typically use a generalized linear model like Logit or Probit for a classification problem. A quite different way to build a classifier is to use a decision tree. Most economists are familiar with decision trees that describe a sequence of decisions that result in some outcome. A tree classifier has the same general form, but the decision at the end of the process is a choice about how to classify the observation. The goal is to construct or grow a decision tree that leads to good out-of-sample predictions. Now, we don't have out-of-sample because I took the full sample, which is not the correct approach, but I'm just really setting up our data set here to run to implement the package R package. So to illustrate the use of tree models, I use the R package R part to find a tree that predicts Titanic survivors using just two variables, age and class of travel. Some of that has come out of our Tidyverse exploration of the data. The resulting tree is shown in figure 1. Now we're going to get a slightly different data set because here I think there's 146 observations where we're going to run the full data set of 1,309. Okay, so let's see. We load in. We should install. So first of all, we probably should install. I already have in the R part installed. I just check R part, RP, ART. Right, that's already here. So I have that package, and RPART. So I have that. I have both of these, RPart and RPlot. Okay, so let's just run that, make it loaded into the library, estimate the model. So there's sometimes of optimization taking place. We're going to treat this as a black box, and then we're going to graph. So the RPart plot is the graph, and then we get a graph. And in our graph is saying, look, we're predicting survival on the basis of class and age. And if you're class 3, yes, that 528 out of 709 died. If you're not class 3, that means you're class 2 or 1. And if you're 16, equal to 16 or over, so that's yes to the left, node to the right. So if you're greater than 16, you come here, and if you're class 2, come here, and 157 out of 249 died. Whereas if you're more than 16, yes, and class 2, no, then 193 out of 315 lived. But if you're not more than 16, you're less, that means you're quite young, and you're not class 3 but class 2 or 1, then 34 out of 36 lived. So you can see if you're class 2 or 1, if you're not older than 16, that means 15 or younger, then chances of survival are good. So this is a simple relatively simple classification tree. We haven't studied what the optimization algorithm is in the background. We're not going to. We just take it as a black box. But this is useful in giving us some kind of flow chart or some idea on how to categorize the different outcomes. Not always predicting as true, because we can see not everybody who was in class 3 died, but 528 out of the 709 in class 3 died. So pretty much if you're in class 3, your chances of dying here are very, very strong, and that's what the ratio here tends to indicate. Another approach here, we can turn off the graph for a moment, is to use conditional tree. Again, I'll go back into Halvarian here just to see if we can find this output. Now, one of the things he finds, again similar to our tidyverse, is those who are younger have higher chances of survival relative to those who are a bit older, and there is quite a range here in terms of the confidence intervals. But we'll look for the C tree. Again, we're using slightly different data, but the C tree, let's just see. Black bars indicate the fraction of the group that survived. Okay, and okay, so the C tree or conditional tree, let's just take a look. There are many other approaches to creating trees, including some that are explicitly statistical in nature. For example, a conditional inference tree, or C tree for short, chooses the structure of the tree using a sequence of hypothesis tests. The resulting tree tend to need very little pruning. The first node divides by gender, the second node divides by class in the right-hand branches. The third node divides by age, the fourth. So you can see the first node, the second node, the third, the fourth, the fifth, the sixth, the seventh, and eighth, so on, right? And the one might summarize this tree by the following principle: women and children first, particularly if they were traveling first class. This simple example again illustrates that classification trees can be helpful in summarizing relationships and data, as well as predicting outcomes. Okay, now I have a slightly different data set here that I'm going to use. I didn't exclude the NAs. And let's run the C tree for a moment and model. And we're going to again examine the class, the sex, the age. These are going to be, and the sibling, spouse, and use these to predict survivorship. And then we plot the output, and then we zoom, and we bring the graph in. Maybe I'll go full screen here. And again, what we observe here to give an explanation. So as we look at sex, if you're male or female, and if you're male and you are first class and you are less than 54, then looks like the lived here, the darkened area here represents those who lived. So if you're a male, first class, younger than 54, then a little bit less than 38% of those, around 0.4%, lived, survived, and the balances perished. However, if you're greater than 54, only a small proportion of those lived, much bigger proportion passed away. If you were male, you were class 2 or 3, and your age was less than 9 and your family size was less than 2, then your chance of survival was quite good. But if there was more than 2 in your family, so if not family size, but if the number of siblings you have or spouses was more than 2, so siblings was more than 2, your chances of survival looked quite bleak. If you were less than 9, good. If you're more than 9, again, things look bleak. If you're female and you're first and second class, your prospects of survival were excellent. So indicated by lived is the darkened part, died is denoted by the lighter part. If you were class 3, again, if you had a smaller family, you seemed to do better. If you had the bigger family, so siblings or spouse greater than 2, you seem to have done worse. Okay. Okay, again, that's a nice way of breaking that down, summarizing some of it's a way of graphically trying to understand the data, and this type of tree, conditional tree, gives us, based on hypothesis testing, gives us some sense of the dynamic going on. There's lots of nuances, lots of interrelationship. And again, just to note, if we take the sum here of each of these variables, right, the nodes, then that adds up to 1,309, right, which is consistent with the number of passengers in our Titanic. So when we look at our Titanic dataset, we had 1,309. So each of these nodes, when we add up together, produce the 1,309.